Welcome to this tutorial where I'll show you how to run the FORCsensei processing package on your local computer. In preparation, I've created a new folder on my system called FORCsensei, and within that folder I've created the data file that I want to process. We go to the FORCsensei webpage and we scroll down and we select the information on running FORCsensei locally. Now, to run FORCsensei on your local system, you will need to install Anaconda, and there's instructions on how to do this. And once you've installed Anaconda, then you can download the FORCsensei notebook, which we'll use for processing the data. The download's very simple. You just do a right click on the link, say download linked file as, and you can see here's the FORCsensei notebook. It has this extension IPYNB because it's a Python notebook, and we're just going to save it into the same folder as our data. If we look over here back in the folder, we can see that the FORCsensei notebook has been downloaded, but for some reason my browser has added a .txt extension. This isn't a big problem. We'll be able to correct that in a moment. So now we're ready to go. We need to start our Jupyter Notebook server, and we can do that through the terminal. I'm working on a Mac, but there's very similar approaches on Windows and Linux systems. So on a Mac, I just go into the Spotlight search. I'm going to start a terminal. I get a new terminal window. I'll make it a little bit larger so that we can see what's happening. And then I just CD into the folder that contains the FORCsensei notebook. So in my case, that's in Documents, and it's in the FORCsensei folder. Now, to start the Jupyter Notebook server, I just say Jupyter Notebook, and that will start a new Jupyter Notebook server. I can now make my browser full screen. So here's my notebook, and here's the data file that I want to process. Now, remember, for some reason my browser's added a .txt. What we really want for this to be identified properly as a notebook is just to have the IPYNB extension. So we can just click the box here, say rename, and remove that .txt. Now, it's possible your browser didn't add that txt, in which case you don't have a problem. But in my case, I need to remove it. And we rename, and you can see everything looks good. So to activate the notebook, I just click on the file, and it now appears as a Jupyter Notebook. Now, if you're not familiar with Jupyter Notebooks, it's really just a way of managing code where we can have cells that contain text that provides an explanation of what's going on, and then we have cells where we include Python commands that we can actually execute within the notebook. So this first cell here is just giving you a bit of information about what's going to be happening within this code cell. So the first thing that happens is we are going to install the FORCsensei package from GitHub, and then we'll import the FORCsensei package into this notebook. And the way that I execute the code cell is very simple. I just press Shift and Enter together. You can see a little star has appeared indicating that processing of that code is taking place. I'm getting some information telling me about the download from GitHub, the installation, and so on. And once it's completed, you'll get a number in here indicating that the code has finished. So everything's installed okay. And now I need to tell, in the next section, tell FORCsensei where it can find my data file. So I already have my data file in my folder. It's here. And I need to include the full path of that data file as well, so that the FORCsensei notebook knows where to find it. Now, on a Mac, this is quite simple. I just go to the folder, I right click, hold down the Option button, and I can say that I want to copy the file as a path name. Then I can go back to my notebook and just paste that path in here, in between the quote marks. So this information is now telling FORCsensei what data file I want to process and where it can be found. And you can do the equivalent on Windows machines and Linux systems and so on. I need to press Shift and Enter again so that this file name and path goes into the memory, and you see a number's appeared showing me that code's been completed. We now get into the pre-processing stages. There's a little bit of Python code here, and if you're not familiar with Python, there's nothing to worry about. You simply press Shift and Enter, and that will initiate the pre-processing options. And I get a menu here that provides me with my sample name. That's inferred from the file name, but if you'd like to change it, you can simply click on the box, type some new text in. I'll just keep it as it was. The next box allows you to perform mass normalization. If the number is -1, that says there was no mass normalization information in your data file, so we'll assume that you don't want to perform any kind of mass correction. But maybe you do. Maybe you know the mass of your sample, it simply wasn't in the data file, in which case you would just add the mass of your sample in grams here. Okay? To begin with, we'll work with a non-mass normalized sample. We're going to do a high field slope correction. This works in the same way as you'd correct a hysteresis loop. We just say what percentage of the maximum field do we want to fit a straight line to in order to remove that high field slope. Here I'm going to use 70% of the maximum field, but based on the slider you can set that to any value that you want. Okay, and I'll work with 70. Here we have a collection of other correction possibilities. It's always a good idea to remove potential measurement drift when working with forks. Often we have a first point artifact. We may have a last point artifact in measurement outliers. In the case of this data file, I don't think I do, so I'll just leave those unchecked. Once I've selected all my options in here, I just go down to the data pre-processing option and hit Shift and Enter. That will read the data file into my system and perform the pre-processing corrections that I've requested above. It then plots the corrected forks, and here are the difference forks that we may use for processing as well. You can see at the moment we have non-mass normalized units, and it could be that after this we said, well, actually we do want to do a mass normalization, in which case we just go up here, put the mass of our sample in, maybe it's 2 grams for example, and then perform the data processing options again. And now it will read in the data again and do a mass correction and provide us with a plot where everything is mass corrected. So you can now see I've got mass corrected magnetizations. Now if you'd like a copy of these images, if I go make my browser a little bit smaller, this graphic has automatically been saved into your folder as an encapsulated PostScript file. So if I just double click this and bring it into the correct window, you can see that this figure has been saved. So it's all automatically saved into the same folder as your data file, and then you can import it and use it for publications and so on. So now that we've pre-processed our data, we can go into the model options that we want to use for actually calculating our fork distribution. To get those model options up, again, I just select the code cell, press Shift and Enter. This processing is based on VaryFork, so these parameters are defined in the VaryFork paper by Ramon Egli in 2013. We've provided a link to it up here, and you can say if you'd like to calculate the fork distribution based on magnetizations, or whether you'd prefer to do it on the lower branch subtracted magnetization data here. I'll just, to begin with, just work with the magnetizations, and here I can set my smoothing parameters in terms of my horizontal smoothing and my vertical smoothing. And what do I want the minimum smoothing to be? I set with the left hand button, and what I want my maximum smoothing to be, I set with my right hand button, up to a maximum of 10. Now, because this is a demonstration, I'd like the calculation to go quite quickly, so I'm going to set these as small values. Similarly, for the vertical, I'll set that as a small value. And for the lambdas, I'll set those to 0. Again, look in the VaryFork paper for clear definitions of what these parameters are. Now, in the tabs, we also have a downsampling option, and that can be that as you're trying to work out what smoothing parameters you should use, you'll actually find the calculation takes a long time. So rather than calculating the distribution based on all of the data points, you can do it on a downsampled version of the data points in order to try and get a feeling of what your smoothing parameters are. And then once you've worked that out, you can then calculate it on the full data set. So to begin with, I'll calculate it on a relatively small number of data points. You can see that the total number of data points is 15,364. To begin with, just an example, I'll turn this right down so that it's quite quick. say 2043. So that will randomly pick 2043 data points from my FORC data set. Processing, this is the number of cores that you have available on your computer. That number will be changed according to the number of cores available on your computer. You can choose to run everything just on a single core. You can choose to run everything across all the cores of your computer or something in between. Of course, the more cores you use, the quicker the calculation will go, but it may slow down other tasks that you're running on your computer. So for this demonstration, I'll run with all the cores on my computer. Once I've set these options, I can now go into the calculation of the fork distribution. I can do this by executing this command here. And once the model is running, I can get updates on the progress of the calculation by following this link, and that will show me how many jobs in the multi-processing are completed, how many jobs are left to do. So I just press Shift and Enter to start the execution. I can now visit this page here, and this is showing me the Dask multi-processing. It's showing me the task stream, the jobs that are being processed, how many jobs are running, how many jobs need to be completed, and so on. And this will go relatively quickly because I've downsampled my data set from about 15,000 data points down to about 2,000. If I return to FORCsensei, you can see I've just got a star next to this command, which means that the processing is continuing. Once the processing has finished, you'll get a number and the graphics will appear. The best explanation of these graphics is to refer to our paper, but to give you a quick idea of what's happening, these are the indications of where the data may be undersmoothed or oversmoothed. This is our phi parameter that we want to try and optimize to a value of 1, meaning that we don't have any undersmoothing and we don't have any oversmoothing. Now, because we've downsampled the data set, we estimate phi via a bootstrap, and this is the distribution of estimated phi values. So there's a 95% probability that our true value of phi for these very fork settings lies somewhere between 0.82 and somewhere between 0.852. And this just shows the histogram on the right corresponds to the points here. How many points do we have that correspond to a cubic polynomial surface? How many points do we have that correspond to a fourth order polynomial surface, and so on? And these are indicators that we can use to try and then change our regression model to optimize the smoothing parameters. And again, I can't go through a detailed discussion of that here, but I suggest that you look at our paper for seeing how that works. We can see in this case we're probably oversmoothed in areas like this where we have pink points, and maybe undersmoothed in some areas as well around the edges. But for the sake of speed, let's imagine that we're happy with these model parameters, and if we wanted to, we could plot our fork distribution, in which case we'd simply go down here and execute the code. But it's giving an error, and the reason it's giving an error is that at the moment our fork distribution is based on a downsampled data set. We only use 2,000 points. So instead, we need to calculate if we're happy with our regression parameters. We need to return to our downsampling menu, turn this all the way to the top so that we're now going to calculate a fork distribution with all the data points and execute the model again. So this will now undertake, using the very fork parameters that we have, a calculation of the full fork distribution across all 8 of the cores on my computer, all of the data points, and these very fork regression parameters. This will take some minutes to complete. Again, we already have our status of the parallel processing available, and as the jobs complete, they will appear across here so that you can get some idea of approximately how long the processing is going to take. Of course, it's not necessary to check on the status. You can simply leave it until it runs. And on a local computer with typical power, you'd be talking some minutes for data sets of this size. If you've got a very large data set, for example, hundreds of thousands of magnetization points, you could be talking 10 minutes or more, in which case it's worth looking at the status just to get an idea of how long the model is going to be running for. So while that model's running, it's also worth me talking about a few other things. Many of the processing techniques and ideas that have gone into FORCsensei have been developed in earlier work. So for example, we have the paper by Pike et al. FORC was developed by Ramon Egli. So as we develop the FORCsensei package further, we will update this reference list, and we would recommend that where appropriate you also include these references in any paper that you're writing, rather than simply saying I used FORCsensei. You provide appropriate credit to the people who developed the techniques that went into the FORCsensei processing package. We can see that this is still processing, and again that demonstrates the importance of being able to use the downsampling option when you're trying to select your regression parameters. If you calculated the FORC distributions using the full set of data points every single time, and you were trying to come up with optimal smoothing parameters, it would take a very long time. So this downsampling option allows you to do things much more quickly. We can refer back to the job status here. We can see there's 60 jobs in total that need to go through the processing. 46 are in the memory at the moment and have been processed. A few more have completed. We've now gone up to 48, 49. So it's relatively slow, but this will give you a feeling for the progress as it goes through. We can go back to FORCsensei. Okay, still processing. Another thing that's worth mentioning while we're waiting for the processing is that in order to get the status page where you can monitor your calculation, you need to have this package here installed on your system. Now normally that will be installed as part of Anaconda, and as soon as you start using the FORCsensei package, this link will automatically become available to you. But if it isn't, and when you click on it, it just says the page isn't available, then you can simply go and install this package and it will become available. So our final model is completed. You can see the plots has been made here with our model fitting diagnostics. We now have the final FORC distribution, and there's a histogram showing where we may have cases of under and over smoothing. Again, as before, this model has been automatically saved into the same folder as your data file. You can just bring it up and again use that in publications and so on if you wish. Now, because we've calculated a full data set, we can get our final FORC plot. Okay, we've got an interactive window here. In order to get the FORC plot to appear, first of all, you just need to change one of the options. So for example, if you say include color scale bar, our FORC plot appears. You can see it's got mass normalized units here. And you can, for example, change the number of color levels that you want in the plot. So I've increased the number of color levels. You can select if you want contours, in which case maybe add a contour to every 10th level in the color scheme. It looks something like this. You can change the thickness of those contour lines if you wish to. You can also change the limits on the plot. So for example, maybe you don't want the left-hand limit to be 0, but maybe you want it to be something else. You can just change that, press enter, and it will automatically update. So you can adjust the limits of your plot like that. And then when you're happy with your plot, you can just say download. And as before, the final FORC distribution will be downloaded as a PostScript file into your folder that you can then take into some other software package and edit if you wish. So that's the conclusion of the tutorial. Hopefully everything's clear, but if not, feel free to send us an email via the webpage and we'll provide you with support if we can, or alternatively you can just email us directly using the email address here in the header information for the FORC notebook.